infinite number of square roots. What is the value of 10 times the square root of everything that's inside times 10 times the square root of everything that's inside times 10 times the square root of everything that's inside times 10 times the square root of everything that's inside, repeated infinitely many times? If you can solve this problem, you can then consider the variation, where instead of 10, we have an alternation of 3 and 5. Another variation is to consider we have 10 under each radical, but instead of just having a square root, we have an nth root. This will be for n is equal to whole number values like 2, 3, 4, 5, and so on. Finally, what would happen instead of one fixed value of this root, we have an increasing value. So we have 10 times the square root of everything that's inside, times 10 times the cube root of everything that's inside, times 10 times the fourth root of everything that's inside, times 10 times the fifth root of everything that's inside, and so on, repeated infinitely many times. I thank Abdel Hakim from Algeria for suggesting this. In fact, the problem with alternating 3 and 5 terms appeared on a math competition for third-year students in high school, which would be about 16 and 17-year-olds. Can you figure these out? Give them a try, and when you're ready, keep watching the video for a solution. Now, before I get to the answer, it's very important that a YouTube channel of my size and reach mention something about convergence of an infinite product. The infinite product of positive real numbers converges if and only if the following infinite sum converges. In other words, if we take the term-by-term natural logarithm and we add up all of those terms, and that is a convergent series, then we know that the infinite product also converges. So this gives a connection between the convergence of an infinite product and the convergence of infinite sums. And most of us have studied infinite sum convergence in class, so we can apply the basic lessons. Now in this video, we're going to be dealing with things which are infinite sums that we're very familiar with, like geometric series. So there's no need to formally check the exact convergence. You're going to see why they converge through the derivation. But if you really wanted to check the details, you can go ahead and check using this formal method. So now let's get to the answers. How do we solve this problem? Well, we'll solve it by considering the partial products. The first partial product will be 10, or 10 to the power of 1. The next term will be 10 times the square root of the previous term. So we have 10 to the power of 1 times 10 to the power of 1/2, or 10 to the power of 1 plus 1/2. The next term is 10 times the square root of the previous term. So we get 10 to the power of 1 plus 1/2 plus 1/4. And this pattern continues, where the nth term is equal to 10 times the square root of the previous term. And when you work it out, we end up with the following pattern. We have 10 to a geometric series. We have 1 plus 1/2 plus 1/4 plus so on, plus 1 to the power of 2 to the n. So now how can we figure out the value? Well, the exponent is a convergent geometric series, and we can use the formula for the sum of a geometric series to get that the exponent will be equal to 2. So all of this is equal to 10 squared, or 100. And that's it. So now it's a little more complicated if you have alternating terms of 3 and 5. Let's consider the partial products. The first partial product will be 3 times the square root of 5, which is equal to 3 to the power of 1 times 5 to the power of 1/2. The next partial product will take 3 times the square root of everything that's inside times 5 times the square root of the previous term. And when you work that out, you end up getting 3 to the power of 1 plus 1/4 multiplied by 5 to the power of 1/2 plus 1/8. Now we can continue this pattern where the nth term is equal to 3 times the square root of everything that's inside of 5 times the square root of the previous term. And when you work it out, we end up with 3 going to the power of 1 plus 1/4 and all these powers of 4 until we get 1 over 4 to the power of n. And we need to multiply all of this by 5 raised to the other powers. We have 1/2 plus 1/8 and so on, where we get 1 over 2 times 4 to the n. So now, how do we solve for this value? Well, we have two convergent geometric series, and we can solve for their values. So we end up with 3 to the power of 4/3 multiplied by 5 to the power of 2/3. Now let's consider if we have the nth root. Well, this is very much like the square root problem. The first term will be equal to 10 to the power of 1. Then each subsequent term will equal 10 times the nth root of the previous term. And we can go ahead and solve for the pattern here, and we end up with a geometric series where the common ratio is 1 over n. So now we can solve for the value of this infinite nested product by solving for the sum of this geometric series, and then we get the answer of 10 to the power of n all over n minus 1. And notice if you substitute in n is equal to 2, you get 10 squared, and that exactly matches what we solved in the very first problem. Now what would happen if we have an increasing nth root? This is a little bit trickier to solve, but let's work it out. The first term is equal to 10 to the power of 1. The next partial product will be 10 times the square root of 10, so we get 10 to the power of 1 plus 1/2. The third partial term will be the second term, and then we have the square root of the cube root of 10. And this works out to be 10 to the power of 1 plus 1 over 2 plus 1 over 2 times 3. And when you work out this pattern, you end up that the next term, or the kth term, is equal to the previous term multiplied by this following nested radical. We have the second root, the third root, and all the way to the kth root of 10. And when you work that out, it ends up being the sum of factorials like this. 10 to the power of 1 plus 1 over 2 factorial plus 1 over 3 factorial, and so on to 1 over k factorial. So now we look at this exponent, and this is another familiar pattern. This is equal to e minus 1 because e is equal to exactly this infinite series plus 1. So this all will be the value of 10 to the power of e minus 1. Did you figure it out? Thanks for watching this video. These math videos, which can be watched for free on